Hi, I'm Prof Joe, and this is part of my lecture on measurement technology. Today again talking about some more sensory stuff, especially talking about mechanical vibrations and the measurement of mechanical vibrations. So, talking about mechanical vibrations, we are into measuring accelerations. Vibrations are correlated to the movement, and the movement is correlated to the acceleration. And so our goal is to measure accelerations, measure fast distance changes and vibrations on a machine. How to do so? The typical idea is we use some inertial mass. So let's imagine our sensor, which has some strain over here, coupled to our mass m, our inertial mass m, and somehow damped in a certain way. So that's the damping. That's a normal spring. Imagine that's a spring the mass is connected to. And now we just consider movements in that direction. And what happens is, so we have the machine over here, which exerts a movement on the sensor, and now the inertial mass will try to keep its position, and so by that we will get a movement of the inertial mass within the sensor. And now you can realize that the movement of that mass is somehow usable, is somehow pointing to the movement of the machine down here. That can be correlated via Newton mechanics in a quite simple way. I won't go into details about the mathematical details. You can use that AI agent below to get those mathematical details. But I will talk a little bit about the behavior of the systems in the frequency range. So we have some resonant frequency over here, and we have some amplitude xe of the movement of the external machine and xa movement of the inertial mass. So we can look at xa over xe to get the correlation of that movement to that movement, and that's interesting for us. And we get something like that. Depending on the damping of the system. So for that, we are at a very low damping area. At that, we are at a damping area of about 1, and there we have some damping area which is large. I will just write down 10, something like that, and we can discuss that behavior. Meaning, for that system over here with no damping, we get a problem of a resonant frequency, the problem of a resonant frequency, meaning the machine moves in such a way that it always puts energy into the movement of the inertial mass, and by that exaggerating that movement theoretically into infinity. So we get a very large movement of the mass, and we don't want to have that. That's for sure a measurement case we are not interested in at all. There are more reasons for that. The next reason would be the amplitudes of that movement and of that movement should be about the same, or we wish them to be about the same. And so for the resonant case, there's no proportionality anymore, and also the other curves are not very linear, so that behavior won't be fulfilled also. So, okay, we need damping. So we can do some over damping, kind of the line here below. That's okay so far, but we don't get a very linear behavior over the whole range. And now choosing the damping to be around 1 in this case. That 1 is some ratio between two other values, but it defines a value of damping we can calculate at least, which is at a very specific place, which gives us the most linear, a linear behavior at the biggest range of the spectrum over here. And that is the thing we wish to have. We want to have a mostly linear behavior, which this damping case fulfills the best. Okay, now we are able to build something like an acceleration measurement device by, for example, measuring the movement over here using a strain gauge. For that, choosing a high spring constant and a high damping to get only small movements, but we can choose for that. And by that, being able to measure machine vibrations, for example. But there are other things we can use that stuff for. Think of your mobile phones. You can turn them around and they will recognize if you're holding it straight up or you're holding it horizontally. That needs to measure the Earth acceleration. Can be done using inertial masses also, extending that system for a second direction and measuring the acceleration in X and Y direction, for example. And so on and so on. There are different, very manifold applications out there of measuring the acceleration or measuring vibrations. Especially the newer times brought along the measurement of the vibration of machines in senses of predictive maintenance. What does that mean? In times back then, people were hearing the machines, and when that sound changes they were hearing, they had the feeling of, oh, that machine somehow gets old. We have to do some changement of some parts which got old and so on. But that was kind of a feeling. And now measuring the vibrations and doing predictive maintenance, nowadays people try to do that feeling stuff more specifically. So measuring the vibrations is something like hearing, but indeed we get an exact spectrum, not just the feeling of a hearing, but a real measurement spectrum. And now, for example, we can look for certain peaks in the spectrum of a measurement. And now if that peaks gets smaller or larger or changes its position, we know something changed in the machine. Something got old, or something got different, or something got broken due to the fact of those changing peaks. And now that allows us to do a maintenance interval depending on the measurement before the system breaks down. We have to do a lot of analysis, but that is something which got introduced over the last couple of years into industries very much. Having said so, those vibration measurements, those mechanical movement measurements got more and more important, especially in senses of that predictive maintenance, and are part of many daily devices we are using, thinking of your mobile phones, for example. See you next time. Have fun.